The confirmation of the existence of supersymmetric particles in our universe is one of the most sought after discoveries in modern physics. With this research, we try to contribute a little to this effort. My name is Pecko.
I'm Marek, Červeň, and now we are standing in the Physics Popularization Center in Martin, Slovakia, in European Union, and this is reduction of number of detected standard model particles in search of supersymmetric particles. To create this project, we had to learn a lot of theory. We had to learn about supersymmetry, about standard model, about molecular physics.
This research led us to the creation of our abstract, which in its whole sounding can be read in our research paper, which is edited together with the video. This research also led us to our first problem.
And the first problem is the presence of standard model particles, or in other words, background, during the search of supersymmetric particles in Large Hadron Collider.
Our solution to this problem was that we would apply the Stern-Gerlach experiment, precisely its non-homogeneous magnetic field, which would siphon out the particles that are creating the background in search of supersymmetric particles.
The theory behind it is that the theoretical spin value of SUSY particles, or in other words supersymmetric particles, differ from their classic counterparts.
The value of the particles which wouldn't be affected by the magnetic field would be those of the supersymmetric partners to fermions or sfermions,
which would have a spin value of 0.
The collision at Large Hadron Collider is based on the fact that protons are made to centrally collide and their constituent particles are scattered. These particles also have their distinguishing features such as wavelength and energy, by which we can differ them.
And our idea is that by the influence of the non-homogeneous magnetic field, we can differentiate the classical fermions and classical particles from the sought-after supersymmetric particles. This can be achieved by application of the non-homogeneous magnetic field, which can differentiate particles based on their spin. The supersymmetric particles, especially supersymmetric fermions or sfermions, have the spin value or maximum angular momentum value equaling 0, which means that they won't be affected by the non-homogeneous magnetic field, and that will create a pocket of space in the Large Hadron Collider where there will be much higher concentration of supersymmetric particles.
Here we can see the division of particles, both of the standard model and the supersymmetric particles, into divisions according to how they are influenced by the non-homogeneous magnetic field according to their spin.
This can be easier seen on this table, because in spite of classical search of supersymmetric particles, now we are searching only of two groups, which one of them are some boson and other are the target particles, sus fermions. Only the bosons of them create the background.
This makes it easier for modern machine learning programs to distinguish the particles from the background. Assuming we know the potential energy of the particle spin magnetic moment, by using these two equations, we can determine the value of force by which the non-homogeneous magnetic field is going to affect the flowing particles in the system.
And we can see that the plus or minus sign in front of the spin, or the maximum angular momentum of the particle, determines the orientation of the force that will affect the particle and the way that it will be, the trajectory of which will be differentiated.
The first problem that we encountered, however, is that this force is going to only affect the particles flowing in one direction, in our case the z direction of the system.
Another problem lies with the untraceability of the individual supersymmetric particles. By the way that the Large Hadron Collider is built nowadays, we can see only the Tótha particles that were made by the dissolution of supersymmetric particles, and from them we can calculate our backwards. In conclusion, our theory has two shortcomings. The first of them is the ability to only measure the change of direction of trajectory in one axial plane.
The other being that we can only measure values of properties of the Tótha particles of our target particles, which makes it harder for our search.
Now we can speak about the future of our project. Our project has two shortcomings, first of which can be solved, and can be solved quite easily, and that is by application of the more complicated magnet, which would create a non-homogeneous magnetic field which affects all particles in each direction and even in all axial planes. The second shortcoming is that the supersymmetric particles don't live long enough to be measured by the classical measuring systems. To solve this problem, we can only create new measuring systems inside of the pocket of space that we will create, and that will ease our search of supersymmetric particles.
Here we can see all the sources that we used for our research. All the sources and their whole sounding can be read in our research paper, which is edited together with a video.
And in the end, we would like to thank you for your attention. If you have any questions, please ask us. We'll gladly answer all of them, and thank you.
Thank you very much.